So hi, I'm Daniel Koch. I'm from the Nvidia driver team. I work on the mobile drivers, the Tegra drivers actually. And I'll be covering Vulkan subgroups. So I'm going to give you a bit of a motivation for what subgroups are, or why you want to use them, give you an overview of how they work in Vulkan, and then go into deep dive onto the various operations. So the various types of operations, how they work. Go into an extended version, partition subgroups that are available on Nvidia, talk some more details about the Nvidia implementation, and give you some tips. And if you're used to HLSL, explain how these map to the Vulkan ones. All right, so motivation. So Vulkan 1.0 and GL and those support sharing data between invocations. So I use the term invocation here. It just means a thread of computation. So like a shader, a lane of computation. You can use sharing data between invocations in Vulkan. In the local workgroup, you can communicate those only between shared memory or going out to other resources like buffers or images, but that's obviously a lot slower. So the fastest way is with shared memory. And the only way to synchronize between these invocations is you can synchronize all of them in the local workgroup. And you can only do this in compute shaders. So with Vulkan 1.1, we've added the ability to synchronize between a new concept called a subgroup. So you can synchronize data directly between those invocations or threads, and you can synchronize between those as well without having to synchronize all the threads in an invocation. And these, it's basically the ones that are running in parallel. So typically a warp or a wave or whatever your favorite terminology is. So the main benefit of this is that you can avoid going out to shared memory. So it can reduce your latency and increase your bandwidth effectively, and you can accelerate a lot of algorithms such as reductions or list building or sorting. And in Vulkan, they're allowed, they can be supported in all stages, not just compute shaders. So back to the basics. What is a subgroup? So a subgroup is a set of shader invocations. A shader invocation is basically a thread of computation. You may have heard of things called warps or waves or wavefronts. It's basically those set of threads that are all running effectively in parallel. So you think of them as running concurrently. They oftentimes are, but they may not actually be. So it's something to keep in mind when you're designing your algorithms to use subgroups. That just keep in mind they may not all actually be run. They may not be running in lockstep. So. Very important. And the other thing to note is that implementations can actually advertise a smaller subgroup than your wavefront. So I'm not sure if any do right now, but I know for Nvidia, our wavefront or our warp is the same as the subgroup size. The other thing to keep in mind is that your invocations, they can be active or inactive. So if they're active, obviously, they're actually executing the code right now. The piece of code that you're thinking about, that instruction that you're thinking about, they're actually executing this. And then there can also be inactive ones. So there's a number of reasons why a thread may be inactive. For example, you could be in non-uniform flow control. So all your threads are executing along. If this condition, well, some of them don't get in there, so they some go through it, and other ones skip over and go through the else condition, for example. So between non-uniform flow control. They're going to be divergent there, so you have to watch out for that. Other reasons you may not have that is in a graphic shader there's various reasons, such as maybe you have a draw call that's a state change afterwards, so they can't your vertex shaders they could run them in parallel if they were using the same state. Possibly they could be processing them at the same time. But if you have a state change, obviously you're going to have to sort of flush the vertex pipeline out, so that's not possible. And the other cases in compute shaders, if you're using, your local workgroup size isn't a multiple of the subgroup size, there's going to be some inactive invocations there. So and you need to keep in mind that these can change through the shader as you execute through the code based on the flow control as it converges or diverges and possibly reconverges. So in Vulkan, there's a number of properties that you can query about that. So first, there's the subgroup size. This first one there's the subgroup size. So that's basically the number of invocations in each subgroup. So it's a number between 1 and 128. I'll get to some common value. Well, so common values are 64 and 32. But they could be down to one, so which isn't really subgroup, but it's basically the trivial case. And the main reason we let it go down to one in Vulkan is to allow you to have a unified code path between implementations that have true subgroups and ones that don't, because this can enable you to have, instead of having a completely different type of shader path, you can still execute the same shader code even if the subgroup size is 1. You can query which stages are supported. So they're optional in all, well, they're supportable in all stages in Vulkan. Only the compute shaders are required, but they're also supportable in fragment, vertex, tessellation, geometry, etc. And supported operations, so there's a list of the operations there. There's a whole lot of them. I'll be going through what they all mean. That's basically what the rest of my presentation will be about, explaining how they work. And the other thing to keep in note is that the only one that's actually required in Vulkan 1.1 is the basic feature set, or the feature bit. And finally, there's the quad operations in all stages. This describes, so one of the sets of operations is quad operations, which is typically used in a fragment shader. But some implementations may support them in other shaders as well. So this is basically, are they only supported in fragment and compute shaders, or can they be supported in all of them? All right, so what are the basic operations? Well, the first thing you need to know is what the subgroup size is. So this is built in the shaders. I guess the other thing to note, I'm going to be talking about using the GLSL syntax for, this is sort of what the native, well, Vulkan itself doesn't have a native high-level language, but we what Khronos uses is GLSL, and so we've written a full extension in GLSL to map into Spear V. And so that's what you get the most full support for. And we also have mapping from HLSL as well, which I'll mention a bit later, and I think you'll get some more details about that a bit later as well. So subgroup size is how big your subgroup is, so that's a constant for the device. It's going to match the query from the API. And the subgroup invocation ID, so this is so you know which within a subgroup, so maybe 32, you're going to know which invocation this particular invocation is. So you can find out. So that ranges from 0 to subgroup size -1. In compute shaders, there's also a mapping from the subgroups to the local workgroup. So the local workgroup is all the threads. So basically, your x times y times z workgroup size. So that's the local workgroup, and then that can be broken down. That'll be broken down into the number of subgroups. So that's basically the total number of invocations divided by the subgroup size, and round it up a little bit. And then you can also get your subgroup ID in that breakdown. So you can, the main reason you want these is to be able to map between the data in a specific thread. If you're going back to shared memory or to buffers or images, you want to find out where I am compared to all the other shader or threads that might be running later. Function-wise, so there's a subgroup barrier. So this is basically a full memory, so basically, and execution barrier. So so by the time when you leave a barrier call, all the stores to coherent variables will have all been completed, at least as far as any other thread in the subgroup will be able to tell from looking at them. And it's an execution barrier as well. So basically, all the threads, all the invocations have to get to that subgroup barrier before any can continue. There's some finer grained ones. There's subgroup memory barriers that basically orders all the memory transactions, so all memory types. That includes buffer, image, and shared. And then there's finally there's individual for different, so you can synchronize based on which types of memory you access. So if you're only caring about shared memory, you can use subgroup memory barrier shared. If you only care about buffer memory, you use the buffer one. So the memory barrier ones, they don't fully synchronize, but they synchronize the memory accesses, so to make sure that if one invocation has written out to the memory, that others will be able to see that memory as it's changed. And finally, the subgroup elect. This basically says, pick me one invocation to go do a piece of work. So it always picks the one with the lowest subgroup ID. And this usually is this if you want to load a piece of data from, if all the invocations want to use the same, same calculation, for example, or if they want to, load or store a result in a bigger piece of data, instead of having every thread need to write out or something, you can just pick one thread to do that piece of work. So the vote operations, this is the next grouping. These allow you to determine if a Boolean condition is met across the entire subgroup. So if you want to know if if you have a Boolean condition, so if value equals 5 or something like that, or value greater than 6, you basically say subgroup all, and then you put the Boolean condition in there, and it'll tell you, that gives you returns if all the invocations are going to hit the same condition, and same for any and for all equal. It's basically the Boolean conditions there. So this is very useful if you have code that's branchy, for example, and if you know that all of the threads are going to go one way, you can perhaps do a more optimized calculation. So, okay, if this condition is met, if all the threads are going to meet this condition, I'll go down this one branch of code. If I know that this other condition is true, we can all go the other way, and maybe if neither of the conditions are true, we have to do a mix of both, and you have to sort of fall into the third case, and you might have to do the most complex calculations that way. But knowing that all the active threads in a subgroup are going the same way can be very useful to help you to save work. So just some examples. So I'm going to have a lot of examples in this presentation. So you see, so I'm just going to be using a subgroup size of 4. It's smaller than most implementations will have, but I don't want to try and work with 32 or 64 on the slides. It just gets unwieldy. And you can mostly understand it from a subgroup size of 4. So for example, so I'm going to have, so in this case, I've got four invocations. The numbers inside them are the data, a specific value in the thread. So we talk about value, it'll be 5, 2, 1, or 6. The invocations I'm always going to have on the left is going to be thread 0, thread 1, thread 2, thread 3, etc. So I'm not always going to number the invocations, but that'll be the order that I'm going to be talking about them in. So just an example with subgroup elect. So you call subgroup elect on the middle set there. It's going to pick the invocation 1 with the value 2 in it. Because the invocation 0 is an inactive thread in this example. So it's not executing right now. So if you say subgroup elect, thread or invocation 1 is the one that's going to continue doing your calculation. An example of the vote. So if you have a condition value equals 5, so for the first line, if you do subgroup all on value equals 5, the first grouping, that's true. Second one's false. Third one's false. Condition equals, value equals 5, subgroup any of them. The first 2 are true, third one's false. And for all equal, so all equal value, so you don't, if you just all equal 5, that would be a bit, literal value, you can do it, but usually you want to do it a specific value, so it compares the values. So if they're all equal, so the first one and the last one, you evaluate the true for that one. Arithmetic operations. So there's a number of these. Basically, these allow you to do an operation across all of the active invocations in a subgroup. The functions are subgroup op. So basically, the operations are add, mul, min, max, and, or, and XOR. So you do subgroup add. It basically adds all the active invocations in a thread and gives you and broadcasts the result to all the invocations that participated in that. So this is usually referred to as a reduction operation, and as I noted, it returns the result of the same calculation to every invocation that participated in that. There's also some operations that operate on invocations. So compared to the current invocation, it operates on the ones that have lower IDs. So basically, a partial subset of them, and so those are called inclusive or exclusive scans. Usually, so there's subgroup inclusive op, so subgroup inclusive add, subgroup exclusive add. So the difference between inclusive and exclusive does your thread, or does the data from your invocation contribute to the calculation or not? So if you do an inclusive scan, it means, okay, I'm going to inclusive add, for example, it means I'm going to add all the values in the lower threads, including my own, and I'm going to store that in my thread. And if you use exclusive, it's just the ones strictly lower. So these are usually useful if you want to do an operation across an entire data set. For example, if you need to do some sort of arithmetic operation across thousands or millions of items, you can set up your compute shader so that it has your local work size is all the items, and then you can do one subgroup at a time. You can do the operation across the subgroup, and then use an atomic to accumulate the result of that into shared memory or something like that. So you not have to, if you didn't have subgroups, you'd basically have to do an atomic operation to do this. So you basically reducing the number of atomics you need by, basically by the subgroup size. So it's potential for massive speed up there. So just an example here. So the first one, we've got subgroup add. So basically, we've got 4 invocations participating. They add all the 4 numbers together, and the result gets broadcast to every invocation. For the inclusive add, so this one's a little more interesting. So inclusive, so it means it's including its own thread in the value. So the first one, there's only one thread, so it includes just gets 3. The second one, it gets all the lower ones, including itself, added together. So it adds together, you get 4. It's brought down here. Result of that carries on, adds to the next one, runs down there. You get 7, and the last one, they're all added together, and you get 9. So the thing to keep in mind, this is an example of how the operations could work. Don't necessarily use the results. This is just for understanding purposes. The exact order of implementations or of operations is implementation dependent. So just keep that in mind. If you've got numerically unstable values, you might have some fun there. Subgroup exclusive add. So the thing to note here is that you actually get the same results, but it's shifted one to the right. They're basically up 1 thread because you're not including your own values. So there is an identity defined for each operation. You can look in the spec if you really care what that is, but for addition, it's 0. So the first one you get the identity value. The first one you get the subgroup, or thread 1 you get subgroup 0, and then so on and so forth. Any questions on that? That's hopefully fairly straightforward. Okay, ballot operations. So balloting allows you to do a limited data sharing across the subgroup. So, and this is potentially faster than going through shared memory. So subgroup broadcast. This basically takes the value from one thread and spreads it out to all the other threads. So the thing with the broadcast operation, you need to have the ID it must be a compile time constant. There's some additional built-ins that don't require that, but for the broadcast, the ID must be a constant. There's also a subgroup broadcast first, so it basically says, okay, pick the lowest active lane and broadcast that value to all the other ones. Again, that's the same semantics as subgroup elect, so you might want to, instead of doing subgroup elect and then broadcast, but you can just do it, basically combines the 2 operations for you. So this is essentially a more powerful form of voting. So you have the subgroup ballot function. Basically, you give it a Boolean condition, and it returns a bit field called a ballot, which has the result of evaluating that condition in each active invocation. So basically, it gives you a bit field, and bit I is set if the expression evaluated to true for subgroup invocation ID equals I, and 0 if the lane is active or if the computation was false. So the reason the UVAC4 is returned, if you looked at some other APIs, they might have just had a uint 32 or something returned. The reason we have a UVAC4 is because we allowed up to 128 subgroups, so invocations in a subgroup, so we need to be able to return, there's no uint 32, or uint 128, so we haven't packed into a bit vec4 of uints. And so the lowest bit of the first vector component, the .x, represents the first invocation. And so invocation 32 is in bit 0, the 33rd invocation actually, numbered 32 invocation is bit 0 of the .y component and so forth. And the thing to keep in mind here is that anything bigger than subgroup size, the bits beyond that are ignored. So the implementation may not look at those components at all. If you only support 32 invocations, it'll only look at the .x component. So that's one of the reasons to use the built-in functions instead of trying to manipulate some of these yourself. And one thing to keep in mind is if you do subgroup ballot true, that gives you a bit field telling you all the threads that are currently invocation in this particular branch of code. So that's often useful to know which ones you can operate on. So as I mentioned, there's some helper functions to simplify working with the UVAC4 bit field, because it's a lot of the built-in functions that we have in the shading languages don't operate across a bit. for bit extraction and so forth, they only operate on one component. So to simplify working with a UVec4, we have a number of built-ins that help this for you, and they can also be optimized on an implementation because the implementation knows exactly how many invocations it's going to be running at once. So if you wanted to write generic code, you'd have to look at all 4 vector components, whereas the implementation built-ins may only look at 1 or 2 of them. So subgroup inverse ballot, it sounds complicated, but it's basically just a simple way of saying, okay, is my current thread, did it evaluate that ballot to true or not? And what you pass into these functions, the value here, the UVec4 value, it's basically just the result of a previous subgroup ballot call. So you can bit extract, bit count to count how many bit, pull the specific bit out so you can check if it was, true or not. Count the number of lanes that the computation evaluated the true in. You can also do exclusive and inclusive bit counts. Those are just like the add operations. They include the lower ones or the lower end self. So if you want to calculate how many invocations of the below me evaluate the true, you can figure that out. And finally, there's a subgroup ballot find LSB or MSB. Subgroup ballot find LSB is basically going to give you the same as subgroup elect. And MSB, maybe you want to know the highest thread for some reason. Just some other helper functions. There's also built-ins. So GL subgroup EQ mask, for example, basically a condition that gives you a mask of all the other subgroups or invocations in the subgroup compared to your own thread, so you can see all the ones that are less than me. The EQ one is obviously just yourself. Greater than, so you can find out, break it down into depending on your workload. So based on the ballot results. So what do these look like? So first one, subgroup broadcast. So I take the value X and I want to broadcast that from invocation 2. So you can see the value of 1 gets split out to all the invocations. Subgroup broadcast first. In the second example there, well, the first invocation was inactive, so we get the data from the second thread broadcast to all the other ones. The top right there, so you have if you have the data 4, 5, 1, and 7, what does the subgroup ballot of value greater than 4 give you? So it gives you bit field of 1, 0, 1, 1. So just remember the bits are listed in the opposite order of my subgroup, so not confusing. Subgroup ballot of true, which shows you which threads are active. So the middle one there, they're all active. The bottom one, only the 2 invocations are active again. So how do some of the helper functions work? So subgroup ballot inverse, it basically tells you, okay, was the bit true or false, or was this computation true or false? Bit count tells you how many threads, so in the first example, in 1101, there's 3 active, so each gets 3. If you do ballot inclusive bit count, so it basically adds up as you go along because it's an inclusive one, including itself. So it gives you 1, 1, 2, 3. If you have on that ballot. And so this is also another way of looking at this is the same as subgroup ballot bit count of value and the subgroup LE mask, less than or equal to mask. And same for the exclusive, or similarly for the bit exclusive bit count. Subgroup shuffle operations. So these are a more extensive way of doing data sharing across the subgroup. Basically, it allows an invocation can read a value, read the same value, of a variable from another invocation. So you can specify if I do subgroup shuffle, and then you can specify, okay, the ID is I want to read this value from this other ID. So this is very similar to the subgroup broadcast, except that the ID can be determined dynamically. So it doesn't have to be a compile time constant in this one. So basically, you can have any thread reading from any other thread in the subgroup based on passing in the ID based on whatever the value is, and so they can redraft that, so they don't have to write the values. So you can completely swap data around between invocations without having to go through shared memory. Shuffle XOR instruction, subgroup shuffle, basically returns. It basically lets you swap a set of invocations using the mask that you provide to it. So each invocation trades with exactly one other invocation, and it's basically a specialization of the general shuffle. That's pretty, but it's a pretty common operation that you need. So in this case, though, the mask needs to be a compiled constant integral expression. There are some special conditions that if you want to use these on a loop, it's a often common thing that you may need to do a loop based on the powers of 2 to do some operation. If you want to swap, all your data for some reason, if you're doing some sort of operation, perhaps sorting or something like that, you might want to do something like that. But if you want to do it in a loop, then essentially it needs to be an unrollable loop. So you need to meet the conditions for that. Just so an example here, so subgroup shuffle with index. So in this case, the index for the invocation is going to be 2, 1, 1, and 0. And so each invocation is going to be, that's the value that they're going to pass in for index, and they're going to end up reading from the different cells or the different invocations. So if you do a subgroup shuffle XOR, so if you pass in a mask of 1, basically, pairwise they're going to swap. If you pass in subgroup shuffle XOR 2, basically going to be every 2 in a quad is going to swap. So shuffle relative is the next group of operations. So this enables you to do shared data shifting. Shifted data sharing, between subgroup invocations. So basically you can do shuffle up or shuffle down. And they let you read from, you pass in a delta, so it's either you're reading up or down from, basically shifting 1 or 2 or whatever appropriate for your algorithm. So these are useful if you need to construct your own type of scan operations, for example. So if you want to do a strided scan, for example, you want to add together all the even invocations separately from all the odd invocations. You can also construct things like a reverse scan because the other scans we had with the arithmetic ones, they went from lowest to highest. Maybe you want to go from highest to lowest for your algorithm. Well, you can construct your own, but actually in this case, it's actually probably more efficient to use the built-ins. So it would actually be better in this particular case to do a shuffle followed by a subgroup inclusive. So you need to think about your algorithms in terms of that to see which makes sense. And example here, so if you're shuffle up 1, basically each piece of data moves up to the next higher thread, and you're kind of left with, you're not sure what on the bottom one, but you need to, obviously there's algorithms that you don't care about that one anymore, for example. Shuffle up 2, everything moves over 2, shuffle down, similar. Clustered operations. So sometimes you want to perform an arithmetic operation on just a subset of your data, or a fixed partition of a subgroup. So the clustered operations are great if you want to add across the whole subgroup, but maybe your particular algorithm you want to add across 16 threads, for example, 16 data values instead of 32 or 64. So what do you do? Well, you can use the clustered operations. So subgroup clustered, add this, same operations as your arithmetic one, add mul, max, min, and or XOR, and you pass in the cluster size. So the cluster size says, okay, for this operation, I'm going to operate on cluster this size of partition. It needs to be a compile time constant, at least a power of 2, and at least 1. And again, only the active invocations participate in that. So basically, this is sharing data only with your closest subset of data instead of everyone in the subgroup. So maybe if you need to do, somewhere this is common is for convolutional neural network. There's an algorithm called max pooling. So maybe you want to take a data set and compress it down to a smaller data set. You might want to take the maximum value out of each 16 values, for example. So you can divide your data into 16 by 16 grid, use a cluster operation of size 16, and then you can output the maximum for each cluster into shared memory or buffer or whatever is appropriate for your algorithm. So example here, so I do a first operation is a clustered add on with a cluster size of 2. So adds basically 2 by 2 and broadcasts to the 2 invocations that participated in that. Second example is a clustered max with a cluster size of 4. So again, here 4 invocations are going to participate in each max, and it's going to write out the value to the same 4 threads that participated in that. And so I just went up to subgroup size of 8 here just because the examples are getting a little more interesting. Need a few more threads to show what's going on. Next, we have the subgroup quad operation. So a quad is essentially a specialized cluster size of size 4. Typically, these are going to be in your pixel shaders or fragment shaders. They typically represent a neighborhood of 2 by 2 pixels in a grid. So this is usually your derivative group that's used for LOD calculations or derivatives. And so we represent these as a quad 0, 1, 2, 3. But they may not be restricted to fragment shaders. They're also supportable in compute shaders, and depending on the quad operations in all stages property, you might actually be able to use them in vertex or geometry or tessellation shaders as well. So what can you do with this? Well, you can do a subgroup quad broadcast. So you basically send one value to all the invocations in that quad. You can do horizontal, vertical, and diagonal swaps within the quad. So what might you use these for? Example is constructing a lower resolution mipmap. You can use these to basically compute the, add all the values in a quad together and divide them by 4 and output a lower resolution mipmap. So there's a subgroup tutorial that Neil Henning, who wrote the most of the extension for this and did a lot of the work for that. He had a subgroup tutorial which I have linked at the end. He's got a neat little example. Well, he's actually got a lot of examples of how these of all of these operations, and so you can see how to do that if you want more details there. But again, just giving some examples, some visual examples. So if you do a subgroup, so at the top I'm just showing them what it looks like in a not fragment shader. There's no specific ordering that's implied by them, other than it's just 4 consecutive invocations. But the swapping is done, follows the fixed pattern as if they were laid out in a quad. So it's when you look at it this way, the horizontal, vertical, and diagonal swaps are basically exactly what you think they would be. And so those are all the built-in operations. There's one additional operation that new extension that Nvidia has recently released, subgroup partitioned operations. So what is this? This allows you to do arithmetic operations across a flexible set of invocations. So it's a generalization of the clustered ones, except it doesn't need to have a fixed size cluster or partitioning. So what you can do, so you can generate a partition. So you call it, there's a subgroup ballot or subgroup partition NV function, which returns a ballot of all the threads which are, that value, that particular value is the same in all the invocations. So if 6 of the threads have if you have a subgroup of size 8 and 6 of the threads have the same value, you'll end up with a ballot that has the 6 bits set in that one. And if you get a different then you get a unique ballot for each set of threads that have the same value. And then you can do operations on the partition, similar to the clustered and arithmetic instructions. You can do partitioned inclusive, exclusive operations, and then you can do partitioned subgroup partition operations as well. So the same set of 8 operations: add, mul, min, max, and or XOR across those. Those that let you do inclusive, exclusive, and reduction operations as before. There's no restrictions on how the partition, how the subgroup is partitioned. It just has to be that if you pass in a partition, it has to be a valid partition. So you can't have more bits set than our active invocations, for example, and things like that. So that's why you generally want to use the result of the subgroup partition function to generate the ballots for that. Just an example of what this looks like. So if you have the subgroup partition function, so we've got, so in this case, it's not, you can see it's not, it doesn't nicely break down in, to pairs of values. And so the ballots that'll be returned from this are going to, in hex 5, 12, 28, and C0, based on the grouping there. And if you do a subgroup partitioned add, and then you pass in the result of the ballot call from that operation, those are going to be the pairs of invocations that operate in that calculation. And just In this case, my partitions are the same size, but they don't have to be. It could have been that four invocations in one partition, and it could have been 1 and 2 and 1, for example. It's completely data determined how many invocations are in a partition. So why would you want to do these? Well, shaders can't really predict that consecutive invocations are going to have related values at all, right? So the fact that you can do clustered ones is great, but maybe you want to group threads that have similar values together. So it's more useful to be able to discover, using the subgroup partition function, invocations which are related and be able to do operations on those. So for example, if you're doing deferred shading, maybe you want to detect pixels that have the same material or light, and maybe you want to be able to fetch some values from your gbuffer. Okay, we know that all these threads have the same are using the same light, so we can load it from buffer in those set of invocations using subgroup elect, and then load it once and then broadcast it out to those set of values or those set of invocations. So this can actually be implemented by any implementation that supports the arithmetic set of operations, basically just by looping over the partition subsets in each flow control. And some implementations are able to compute all subsets in parallel, and so it's a bit faster. And again, most implementations could probably do a bit better than trivial looping as well, based on implementation, knowing how the implementation works. So just some general details about NVIDIA subgroup implementations. So not under NDA here. So essentially, what our native hardware instructions for subgroups are what's documented in the GL extensions for shader thread group shuffle and shader thread group, shader thread shuffle and shader thread group. Basically, we've got native shuffle, shuffle up, shuffle down, shuffle XOR instructions, and their fast instructions. So those are basically our primitives that the other subgroup operations are built up of via relatively simple transforms. So, on NVIDIA, don't be afraid to use the shuffle operations, because that's what we're using for everything else. So if your algorithm can use the more general shuffle ones, go ahead and use them. And we don't have any major cliffs in our subgroup operations, so all the subgroup operations are relatively similar cost. So if you need to do a reduce operation, it's basically, you can basically build up the reduce operation is basically a set of shuffle XORs to swap your data around and then do the operation on it. There is some slightly more expensive handling of inactive threads in some cases, but I will not get into details on how that's done. Some tips for working with subgroups. So if you're doing it in a compute shader, you want to make sure your local workgroup size is at least the size of a subgroup, ideally multiples of it, integer multiples of it. You want to be fully packed if possible. Common subgroup sizes are 32 on NVIDIA and Intel, 64 on AMD. Yes, I know a subgroup size of 1 isn't very useful, but it does make it possible to have a single code path, so you don't need to have different set of shaders based on if the subgroup size is 0 or 1 or bigger. Subgroup operations, if you use like a subgroup operation, it's an implicit implicit execution barrier. So basically, all the threads have to get to that point before any of them continue. For example, if you're doing like an arithmetic operation, obviously all the values have to be available at the same time to do that. Operations only act on active invocations. So this is very important to keep in mind, and also being aware of your inactive lanes or out of range invocation IDs. If you read from those, you're going to get undefined values in most cases, and things are just going to be weird. And if you're running in a fragment shader, helper invocations will participate in a subgroup operation. So while they don't store to memory, you're going to get some extra threads that you may not have thought about with the helper invocations. The ones, for example, if you're on the edge of a triangle, your pixels are always going to run in groups of 4 in the quad. So if they may be helper, so the ones for the inactive lanes are the ones that are fall outside the triangle are called helper invocations. How does this compare to the shader model 6 operations? So D3D, they're called wave ops. We call them subgroups. D3D, they range between 4 and 128. In Vulkan, we have between 1 and 128. D3D and HLSL requires them in pixel shaders and compute shaders if you have the subgroup function or the wave functionality at all. In Vulkan, they're required in compute shaders. They're optional in fragment vertex tessellation geometry. Most of at least the desktop implementations are going to support them on all stages. Data types listed there, I'm not going to go through them. There are a few more supported in D3D. Some of the types we don't support yet in Vulkan shaders. We're looking at that for the future. Without getting into details on the roadmap, and in Vulkan we have a more complete set of the intrinsic. So we have inclusive scan. D3D only has exclusive. We have clustered operations. We have execution barriers and memory barriers. And we have more helper routines for working with the ballots, for example. I have these here, the mapping between what's your HLSL intrinsic, UGLSL intrinsic, and your subgroup Spear V operation. I'm not going to go through these in the presentation. You can look at those there for offline reference. Where can you get this? Well, it's implemented in GLSlang if you're using that for your shaders. You can use GLSlang with Vulkan 1.1 to compile GLSL shaders. If you like HLSL, which a lot of, I know, desktop developers tend to, you can use the HLSL backend from GLSlang, or you can use DXC. I believe there's going to be another presentation which will talk more about those if you're interested in that. So they're supported in Spear V 1.3, which is required by Vulkan 1.1. And if you're interested in your Vulkan support for your favorite GPUs, you can look under vulkan.gpuinfo.org. So it's very useful. And for Nvidia, AMD, and Intel, we're all shipping them in our Vulkan. They're all required in Vulkan 1.1 drivers, and we're all shipping non-trivial implementations. So we support most of the operations. Nvidia supports all of the operations in all the shader stages. And you can look up the caps for other implementation. I think Intel supports all of them. I believe last I checked, the AMD ones didn't support the arithmetic and the clustered ones, I think. So, but don't quote me. References, so the tutorial I mentioned is the very first link. Specs to the API spec and the shading language specs. Links to the D3D ones and some other blog posts that were related information. Thank you to these folks. So Neil Henning, he was the one who, from CodePlay, he spearheaded getting these into Vulkan 1.1. And thanks. And he also implemented GLSL support. And Lei Zhang, who's going to be talking a bit later, implemented DXC support. And Jeff Bowles and peers from Nvidia, they worked on driver implementation there and helped me review the slides. So in general, if you have Nvidia Vulkan driver questions or issues, Nvidia support or Vulkan support at nvidia.com. We want to hear from you. If you have problems with the drivers, please contact us. Any questions on subgroups?
Hi.
Hi.
On some hardware, there's some limitation of the shuffle XOR that cannot cross 32-bit thread, 32 thread for accessing. Does this apply still with Vulkan? I mean, this is our hardware limitation. So you cannot do a XOR of the address of lane 1 that will access lane 63, for example.
Right.
When XORing.
When XORing, okay.
Yeah.
I guess that's only, you'd have to talk to AMD about that, I guess, because I think they're the only ones that expose subgroup size of 64. I know NVIDIA only supports 32, so obviously not an issue there. I don't know if that's an issue for AMD or not. So.
And you cannot have your group size, I guess, bigger than your group. Like
like your cluster size can't be bigger than the subgroup size, obviously,
okay.
Right?
Thanks.
You touched lightly on it when you mentioned the helper lanes.
Yes.
But on a pixel shader, on a fragment shader, is there any way you could use any information that's passed into the shader to determine if, for example, all the invocations are for a specific draw call? So if you have like mixed if you guys pack
Right.
the waves with different draw calls, can we infer any information from using one of the GL underscore?
I mean, there's the draw ID. I guess that would something like that would probably be possible to do that.
Okay, okay. So that's exposed, so you could use the draw ID and the instance ID to
Yeah, I
determine.
think those are available in the fragment shader, so you'd potentially figure something out there.